Welcome to The Explainer. Today, we are diving deep into a really clever data structure, one that's absolutely fundamental to how massive systems work as fast as they do. We're talking about the Bloom filter.
So here's our roadmap. We're going to start with a problem that is super common and honestly pretty frustrating in computing. Then we'll introduce this really elegant solution, break down exactly how it pulls off its magic, and then, this is the cool part, we'll see how this one clever trick powers a real-world system that you've almost definitely used today.
All right, let's set the stage. Because before you can really appreciate just how brilliant this solution is, you got to understand the problem it's solving. And trust me, it's a big one.
I want you to put yourself in the shoes of a system like Google's BigTable. You're responsible for literally terabytes of data. A user makes a request for one tiny specific piece of that data. Where do you even start looking? It's the ultimate digital haystack problem.
Okay, so the most obvious approach, right? Just check every single file. But at this kind of scale, that's a total non-starter. It would mean a huge amount of disk I/O, and in the world of computing, reading from a disk is like trying to run a marathon by crawling. It's just painfully slow. So the real challenge, the big insight here, isn't about finding where the data is, it's about figuring out as quickly as possible where it isn't.
And this is where the genius of the Bloom filter just shines. See, instead of demanding a perfect, 100% certain answer every single time, it takes this really clever shortcut. It's all based on probability. It's about harnessing the power of maybe.
Now, I want you to really zero in on the wording here, because it's a little lopsided. A Bloom filter can tell you with absolute 100% certainty that something is not in a set. But it can only say that something might be there. This asymmetry, this trade-off, is exactly what makes it so powerful.
And this really lays out the core deal we're making. We're giving up a tiny bit of certainty to get back a massive amount of speed and save a ton of space. It's designed to accept the possibility of a false positive, thinking something is there when it actually isn't, to completely, utterly eliminate the chance of a false negative. That's the one thing it will never, ever do.
So you're probably wondering, how does this thing actually work? What's the trick? Well, let's just build one from the ground up and see what's going on under the hood.
Believe it or not, there are only two ingredients to this whole thing. First, you have a bit array, which is just a fancy way of saying a long line of zeros. That's it. Second, you need a few different hash functions. Now think of a hash function as a super consistent magical device. You can throw any piece of data at it, a word, a number, a whole file, and it instantly spits out a number. That number corresponds to a position in our array. And the absolute key here is that the same input will always give you the exact same output, every single time.
So we start with our bit array. In this example, it's 20 bits long. It's a totally clean slate. Everything is set to 0.
Adding something to our set is a super simple two-step process. You just take the element, you run it through your hash functions to get a few numbers back, and you go to those positions in the array and flip the bits from a 0 to a 1. That's literally all there is to it.
Okay, let's do one. We'll add our first element, the letter P. We feed P into our three different hash functions. Let's say the first one gives us the number 4, the second one gives us 8, and the third one gives us 18. So we just go to those three spots in our array, 4, 8, and 18, and we flip those bits to 1. Our filter now has a memory of P. All right, next up, element Q. We do the exact same thing. We run it through our hash functions, and this time they point to positions 1 and 13. We flip those to 1. Now notice what's happening. The bits we flipped for P are still there, untouched. The filter is cumulative. It's now storing the combined digital fingerprint of both P and Q.
Let's do one more. Element R. It hashes to positions 5, 14, and 19. So we flip those bits, and there you have it. This simple little array of zeros and ones now contains the combined memory, the shadow, of all three of our elements, P, Q, and R. So we've put things into our set. Now for the important part. How do we check if something is already in there? Well, the process is going to look really familiar.
To check for an element, you don't actually change anything in the array. You just take the element, run it through the exact same hash functions you use to add things, and then you just look. You check the bits at the positions the hash functions point to.
Okay, this right here is the heart of the whole thing. So let's really lock this in. When you check an element, you hash it, and you look at the bits it points to. If even one of those bits is still a 0, then game over. You have a 100% dead certain answer. That element was never, ever added to this set. It's impossible. But
If all the bits are 1, then you get your maybe. It's probably in the set, but there is that tiny chance that those bits were flipped on by a combination of other elements, and that small chance is our false positive.
Let's run a test. We want to know if element X is in our set. So we run it through our hash functions. They point to a few positions, but wait, look at that. One of them points to position 11, and that bit is still a 0. We can stop right there. No more work needed. We can say with absolute certainty, X is not in our set. We just saved ourselves a potentially very expensive search.
So, why does all this theory matter? Let's bring it back to the real world and see how Google's BigTable uses this exact data structure to get some truly incredible performance.
So remember the problem we started with? BigTable lives it every day. Its data is stored in these files called SSTables. To find one piece of data, it might have to look in dozens of these files, most of which are on a slow disk. That's a huge performance bottleneck.
So what's their brilliant solution? You guessed it. They attach a small, lightweight Bloom filter to each and every one of those data files. So before they even think about doing that slow, expensive disk read, they do a lightning-fast check on that file's Bloom filter, which is already sitting right there in fast memory.
And what happens? If the filter screams back, definitely not in the set, BigTable just completely skips reading that file from disk. It doesn't even bother. The impact of this is just enormous. For a lot of applications, this one tiny in-memory check can eliminate the vast majority of those slow, unnecessary disk reads. We're talking huge performance gains.
And that really is the payoff, right? A tiny amount of memory, something cheap and fast, saves an enormous amount of slow, expensive work. It is the perfect example of using a clever probabilistic shortcut to dramatically speed up an entire system.
And that leaves us with this final thought. By being willing to embrace a small, controlled chance of being wrong, Bloom filters allow our systems to be massively more efficient. And it forces us to ask a bigger question. Where else in our digital lives, and maybe even our real lives, is a clever maybe actually better than a slow, expensive definitely?